So this is the Topology 2 lecture in the Math in Moscow program. And it's basically the combination of two lectures, lectures 9 and 10 from the booklet. And this is all called cohomology. So what is cohomology? Cohomology is a theory which is dual to homology. Dual in the sense of linear algebra. When you studied the linear algebra course, you learned so I'm starting over again. This is the Topology 2 lecture in the Math in Moscow program. The lecture is a combination of lectures 9 and 10 from the booklet. And the whole thing is called cohomology. So what is cohomology? Cohomology is a theory which is dual to homology in the sense of linear algebra. You remember from the linear algebra course that to each vector of the linear space, you assign its dual, which is called a covector. And what is a covector? It's a function on vectors, a linear function on vectors. So we're going to do the same thing with homology theory. Let's begin with some exact definitions. Main definitions. Suppose X is a simplicial space. G is an abelian group. Then we define the co-chain group CK X with coefficients in G as the set of all homomorphisms, or rather the group of all homomorphisms of CK X G to G. Now notice that the index K, the dimension of the chain, has been lifted from the bottom, where it was for chains, to the top, where cochains. In general, when we pass from homology to cohomology, what we do always is to raise the indices and reverse the arrows. About reversing the arrows, we'll see how it happens in a moment. Where if we have a cochain, so again, a cochain is a function from the chain group CK to G. And we have a chain CK So then we use the following notation. By CK, comma, CK, in angle brackets, we denote the value of CK on CK. So this value is what? It's a number, or to be more precise, it's not a number, it's an element of the group G. So what we obtain is a group of cochains of dimension K of the synthetic space X with coefficients in G. Now we can define a co-boundary operator, delta, which takes CK of XG to what? Well, I mentioned that we have to reverse the arrows. So it will not take this to CK minus 1. It will take this to CK plus 1 of XG. How does it do this? How is this defined? Well, it's defined in the only possible way that can be done. So we want to compute dk of some chain CK, cochain CK. So we must define its value on a chain of what dimension? Of dimension K plus 1. So this is what we must define. And if you think a little bit, you will see that there's only one reasonable way of doing this. We take the value of dck CK on what can it be defined on? It can be defined on CK plus 1 because it lives here. So this is the definition of the co-boundary operator. And now we have the following lemma. Which is a kind of Poincare lemma. And it says that if we do the co-boundary operator twice, then we always get 0. So let me give a proof of this. So we have to prove, we take d of dck of CK and what will that be? That will be a chain, a cochain of dimension k plus 2. So we must apply it to some chain of the form of dimension ck plus 1. So we apply that to this. And what do we get? Well, by definition, we have d of this must be applied by this definition. D of what we had here, D of CK A must be applied oh, I'm sorry. Let me go back one step. Sorry. So this is not, I've rewritten the same thing twice. The definition is this. We apply D of CK to to the boundary. So we apply CK, The only way of doing this is to apply CK to the boundary of CK plus 1. Sorry about that. Let me come back to this point. This is the definition of the co-boundary operator. It's the only possible one. In order to apply the co-chain CK to a k plus 1 dimensional chain, we apply the co-chain CK to the boundary of the chain CK plus 1, which this is a chain of dimension K. So this formula makes sense. It's defined here. And this is the definition of the co-boundary operator. So I'm coming back to this item here. So this is by definition equal to the boundary of CK plus 1. So I have to erase this. And in its turn, this is equal to CK applied to the boundary of CK plus 1. And of course, this is 0 because of the standard, the usual Poincaré lemma. So the definition of the co-boundary operator is perfectly natural. The fact that the co-boundary operator has the Poincare property that D composed with D is equal to 0. It gives us the possibility of defining the cohomology groups as follows: H of K of a simplicial space X with coefficients in G is by definition the quotient group of the kernel of this D here by the image of the other D. And now, to get things straight, let me write out the cochain that we have in this situation. We have CK XG, which is mapped to CK plus 1 of XG by delta K. So here we have delta K minus 1. And here we have CK minus 1 XG. And so the correct indices are the kernel of dk by the image of dk minus 1. If you remember, for the definition of the homology group, here you would have a delta k plus 1. Here the sign is minus because the arrows all go the other way. Another notation for this is to write this as Z X G K by B K X G. Here, the elements of this group are called cocycles, and the elements of this group are called coboundaries. So we have obtained very easily dualization of the notion of homology group. Now let me erase this. And state the following theorem. Which says that if G is the additive group of a field, then H K of XG is the dual space of HK XG. Now you see, if G is the additive group of a field, then these groups here, the co-chain groups, the co-cycles and the co-boundaries, as well as the homologies, are linear spaces. And as such, then the very definition of cohomology group says that what we obtain is the dual to the homology group. This is not really a theorem. This is just a restatement of the definition of the cohomology group in the case when G is an additive group of a field. Now this theorem has the following consequence. If the dimension of the linear space HK, the homology group of XG is finite, then HK of XG is actually isomorphic to HK of XG. So when we look at these two statements, the natural question is, why are we doing all this? We're getting nothing new in this situation. Dualization just gives us the same statements, the same objects, only in a different guise. They are now called cohomology groups, but actually they're the same as the original homology groups. However, we will see that a little later, the advantage that cohomology has over homology has to do with the fact that it's possible to introduce a multiplication operation in cohomology in a very natural way. But now let us consider the question of functoriality. Now suppose we are given a simplicial map F of a simplicial space X to a simplicial space Y. So this is simplicial. Then this leads to a homomorphism of the corresponding cochain group to the cochain group of the other space. Please notice that here the arrows are reversed, because here we go from x to y, and here we go from y to x. So this is reversed. And this is defined in the only reasonable way that it can be done, namely, we just write, supposing we have an element of this cochain group, which is a cochain CK, and it is assigned to some, so I'll put an X down here, to some chain CKY. Then CKY, sorry, this is CKY, and we're going to CKX. So we have to define this CKY. We do it in the only sensible way, namely we'll write CKX of some simplex it's a chain consisting of a simplex. We put this equal to the only thing that it can be equal to. We apply F to the given simplex. And we get a simplex in Y, and to that we can apply CKY, which is the known, the given cochain here. And so in this situation, we have what is called functoriality, although it should be called cofunctoriality. And what does it say? It says, first of all, that if we do the identity of X, then the corresponding, I'm sorry, once we have this, once we have this homomorphism, then we can pass from the chain level to the homology level in the usual way. I will not write up on the corresponding formulas. You do it just the same way that we always do things here. So the identity, and in that case, well, let me actually write F star of H K Y X Y G to H K X G. Okay, so so the identity the homomorphism corresponding to the identity is exactly the identity of the corresponding cohomology group. The identity of the cohomology group and of X G. So here we should add, and this should be K, and this would be K here. So That's the first property of functoriality. And the second property is the following. If we do f, and we do g, and then we do f, and we consider the induced homomorphism in homology, then this is equal to g star f star. Notice that here we have interchanged g and f. Here we first do g, then we do f, and here we first do f star, and then we do g star. So this is a functoriality. So we have constructed a functor from the category of simplicial spaces to the category of a abelian group. Another one, this functor is called the cohomology functor, and it is a contravariant functor. Okay, so much for the definition of cohomology. And now let us go on to the next part of the lecture and discuss the properties of cohomology, which are, as you can expect, dual to the properties of homology. And so this part of the lecture is going to be rather dull. I will be dualizing the properties of homology, which are also known as the Rhode axioms. And in the process, I will be constantly doing,
Oh, there is no problem. We still can see you and hear you.
The picture seems to be lost.
Oh, but we can still see you.
Do you have a picture?
Yeah.
Unfortunately, I don't have it on my computer, but now you see me moving, yes?
Yes, yes.
I'll continue the lecture.
Okay.
Only that I will not see on my own computer screen what's going on, but
okay.
Okay. So let's continue.
Sure.
So this will be section 3, properties, or Rhode, Berg axioms for cohomology. So we are considering a functor, which we have just defined, I will denote it as x h star and star upstairs from the category of simplicial spaces two graded abelian groups. Now, what does this functor do? It does lots and lots of things. And let's list them all, one after the other. First of all, to every space X, it assigns a group H, K, X, G. Now, to every pair of spaces XA, it assigns a group called the relative cohomology group X, A, G. Now, what else does it do? Well, if you have a simplicial map, F from X to Y, to that, it assigns a homomorphism Fk. Notice that the index is upstairs with a star, also upstairs, from H, K, Y, X, Y, G, to H, K, X, G. You have noticed that the order of X and Y has been interchanged. Similarly, for a map G of a pair XA to a pair YB, to that we assign, well, you know what we assign. I won't write it out. And finally, the last thing that I want to mention is that to every pair XA, it assigns an operator, homomorphism, of V H K A, coefficients in G, to H K plus 1 of X A G. I did not explain how you get this and how you get this, but it is perfectly straightforward and simple. You just dualize what you had in homology. Notice that here, the indices have been raised, the arrow has been interchanged, and so instead of going from XA to this D star takes us from the absolute homology group of the smaller space to the relative homology group of the pair. Okay, so this is what our functor does. Now, let's start listing its properties. So the first property is called dimension. This is not this one. It's called dimension. And it says that H zero of a point with coefficients in J in G. I will stop writing G in all these formulas for simplicity is equal to G. The second property is called commutation. And it says the following. You have the following commutative diagram. H K of XA, which, as we know, if we have a map F of pairs, this is mapped by Fk to H Y B. So here F is a map of pairs from XA to YB. Then the induced homomorphism is in the opposite direction and goes like that. Now we're interested in how it behaves with respect to the co-boundary operator. H K plus 1. So here we have delta star. I won't write the index. HK of A. Here we have this arrow, which is F restricted to B, the whole thing, star, K star. And here we have H. I forgot to write K here, K plus 1, B. And here we have delta star. I will not write the index. So we have the following commutative diagram. Now in the booklet, this is completely written completely wrong, because what happened when I was typesetting the booklet, I began by writing the formula for homology, and after that, I intended to lift the indices and reverse the arrows, and I forgot to do it. So the formula for commutation in the corresponding page of the booklet is completely wrong. And I did not notice that until I started preparing for this lecture. And so you don't have that misprint in the list of misprints in the booklet, which I handed out. Okay, so let's go on. So that's two properties. Let us consider some other properties. The next one, very important property is homotopy invariance. I will not write out what it means. The next one is exactness. And it says that the sequence of cohomology groups is exact. Namely, we have the following sequence. Here, let me see where I want to begin. I want to begin at H n plus 1 of, so we have a pair. For this pair, we have the following sequence, which turns out to be exact. H n plus 1 of x. And here we have I star. Here we have H n plus 1 of the pair XA. I have stopped writing the coefficient groups. H n of A. Then we have I star. This is called J star. And this is the most important one. That's the delta star. D star that appears here. And so on. Well, let me write this one. H n of x. And so on. And I would like to write out the up to the very end. And at the very end, we have H0 of the pair. So this sequence is exact. The proof is simple. It's by dualization of the corresponding statement for homology. And finally, the last of the axioms is excision. It says the following: if you have an open set U, which is of course contained in its closure, and that is contained in the interior of A, which in its turn is contained in A, then in this situation, we have H n of x A is isomorphic to H n of x minus U A minus U. Okay, so that is some of the properties of the cohomology functor for simplicial spaces. Now we can define the cohomology functor for singular, for topological spaces by dualizing singular homology theory. And then we have analogous properties or axioms, whatever you want to call them. We also have similar uniqueness theorems as we considered before. Okay, so now we come to the important place. Up to now, what we have done is dualize things that we knew before. So nothing interesting, nothing new has been achieved. Now we begin the new stuff, and we're going to define multiplication. But to do that, we need a slight technical change of the notion of homology. And so we're going to consider something which we will call ordered homology. So let X be a finite simplicial space. Then let us recall that in the ordinary homology theory, we consider oriented simplicities. So each simplex is oriented. Now, to each such simplex, we're going to assign a number of simplices, which will denote as follows. They are ordered which means that there is a fixed order from left to right of vertices, V0, V1, and so forth, Vn. And also, repetitions are allowed. For example, we have the n-dimensional simplex with vertices V0, 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 n times, or n plus 1 times, and this is still a simplex. For these, so we have two chain groups. We have chain group CK of X G And to this chain group, we have a sign. There's no homomorphism, just an assignment of CK of X, G, and we're going to put a hat on the CK to indicate that is the chain group of ordered syntheses with repetitions allowed. Now, even if X is a finite simplicial space, these chain groups can be of any dimension and will be not zero because we have a simplex of dimension 75 million of the form V0, 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 etc., V0s 75 million times. And that gives an element of this group. So to the left, the chain complex of ordered simplicial spaces with repetitions is infinite to the left. This one becomes zero when k is large enough. This one becomes infinite to the left and is non-zero. In fact, gets bigger and bigger as we go away to infinity to the left. However, we have the following remarkable theorem. Which says that CK and CK hat have the same homology. Well, you may want to ask, what is the homology of this chain complex? The boundary operator is defined formally exactly in the same way as the boundary operator for ordinary chain complexes. Now, the proof of this theorem is not at all trivial. And let's see, how much time do I have? I have very little time. So I will not go into the proof. I will only say that the proof involves some non-trivial ideas which we have already studied in a different context. Namely, we use chain homotopy and the cyclic support lemma. In detail, if you want to read this, this is written up in the Prosylov book. Elements of Homology Theory on pages 60 to 61. So it's not very complicated, but it does involve two non-trivial notions, which we have fortunately already studied. Now that we have this finite simplicial space, we have ordered homology, we're ready to introduce multiplication. In order to do that, we need to impose restrictions on the group G. Yes, Monica? Hello?
Sorry?
Um, uh, I thought you said something, but apparently not.
No, no.
What we need at this point, so this is multiplication. Which is also known as the cup product. To define it, we will need to specify that G, the group that we're considering, is G is a commutative associative group with unit. And we're going to denote this group by R. So now we're ready to define the product, and we do this as follows. So it's a product, and it takes a pair of C, P, X coefficients in R, whose C, Q, X, R, so C, P plus Q, X, R. And it does this in the only reasonable way that it can be done, namely, we write CP. So this is a cochain from this group multiplied by CQ, which is a cochain from the other group. And we apply that to a P plus Q dimensional simplex. Let's denote it by V0. And so on. V, P plus Q. Now notice the round brackets here. We have these round brackets here, which tells us that this is an ordered simplex. So the value of this is, by definition, the only reasonable thing that we can write in this case. So we apply CP to V0 and so on, VP. We know how to do that. And as the result, we get an element of R. This is an element of R, of our ring. This we multiply by C Q applied to VP and so on, VP plus Q. So the value of a cochain from here is defined by using this pairing. And these two pairings here. So this is just the product of two elements of the ring. And this is why we needed to have a ring structure so as to be able to multiply these values. For example, R can very well be the group of integers, or the ring of integers. And this works very well for the ring of integers. So this is the definition of the a product of two cochains of dimension p plus q. The result is a chain, a cochain of dimension p plus q, defined in the following way. Its value on a p plus q dimensional simplex is given by this formula. And of course, from a simplex, we extend to chains by linearity, as we always do. Then we have the following lemma. This lemma is a kind of Leibniz rule, except it has a sign. So if we apply the co-boundary operator to the product of these two chains, what we get is the co-boundary operator applied to CP multiplied by CQ plus, and then we have a sign. And the rest is CP multiplied by the co-boundary operator of CQ. And the sign, I think it should be Q. Yeah, it's probably Q, but let me check. No, I have written P here. Okay. So this is checked by direct computation. And a corollary of this lemma is that is that the operation of cup product can be carried over to the cohomology level. As the result, what we obtain obtaining a so what we obtain, this thing is a graded skew commutative ring. And I forgot to say what skew commutativity means. Let me write it up separately here. We have the following fact, which can even be called a theorem. Which says that if we take, well, I'll write it this way, alpha multiplied by beta. This is an element of the k-dimensional cohomology group. This is an element of the p-dimensional cohomology group. This is of the q-dimensional. So I'll just write here H P. This belongs to H Q. Then their product is equal to -1 to the power, I think Q, yes, Q, multiplied by beta alpha. Is that correct? No, it's not correct. It's PQ. Here. Okay. So we have obtained an additional structure in the graded graded abelian group of cohomology. It is not only a graded abelian group, it is a graded skew commutative ring, which means that if you have elements from groups of different dimensions, then their product lives in the cohomology group of the dimension, which is their sum. This here belongs to H P plus Q. Okay, so we have introduced the multiplication operation And now I will go on and explain what a Poincare duality is. It is one of the really most beautiful and extremely unexpected properties of manifolds discovered by Poincare. And what it basically says is that if you have a manifold, a smooth manifold, then it is in a certain sense symmetric with respect to its middle dimension. This means that it's, roughly speaking, under certain conditions, the k-dimensional cohomology groups, or homology groups, are isomorphic to the n minus k dimensional homology group. And this is proved by a beautiful geometric construction, very simple, which I'll have just enough time to explain before this lecture ends. So incidentally, if we look at the booklet, we're already in lecture 10. You will not be able to copy this picture from the board, but a very similar picture appears in the booklet, so you can look at that when you revise the lecture. Now, we're going to construct a bijection. So this is Poincare duality. We're going to construct a bijection between simplices delta ki and certain cells, which I'll denote by delta n minus ki. What do we have? We have Mn, an m-dimensional, smooth, compact, oriented, connected manifold. We know that by a theorem of Munkers, any smooth manifold can be triangulated. And so we fix a triangulation of the manifold. This triangulation is shown as in blue on this picture here. After that, we do a barycentric subdivision of this triangulation. The barycentric subdivision is shown in green lines. I hope you see them from where you're watching this lecture. Now we can construct the following assignment. Let us choose, so to any k-dimensional simplex, we will assign an n minus k-dimensional cell. let's begin with k equals 0. So we have this zero-dimensional simplex here. It's a vertex of our original triangulation. So the n-dimensional cell that we assign to it will consist, by definition, of all the simplices that have this fixed point as a vertex. So it looks something like this. So this is the corresponding cell corresponding to this vertex. If we take some other vertex, say this one, then the cell that corresponds to that will look like this. Now, what do we assign to a one-dimensional simplex? So, for example, let us take this one-dimensional simplex here. We will take its barycenter here it is, and assign to it all the n-1 dimensional simplices of the first barycentric triangulation that contain this simplex. There are two in our case. Here they are, this one, this is the second one. So the dual cell, the dual cell to this one-dimensional simplex consists of two one-dimensional simplices like this. Let me make this a little more. So we have this in red. So what do we assign to an n-dimensional simplex? So let's take an n-dimensional simplex, for example, this one. I'll show it in black. Then to this n-dimensional simplex, we assign the barycenter of the simplex itself. So we have obtained a one-to-one correspondence between the simplices of the original triangulation and the corresponding cells. Therefore, we have a one-to-one correspondence between the homology group C and M with coefficients in R and C n minus k of m with coefficients in R. Now recall that R is a commutative, associative ring with the unit. Now this is very nice, and one immediately thinks that, oh, great, now I will just consider the homology of these two chains and show that they're isomorphic and prove Poincare duality. But no, this does not work for the following reasons. Because if we write out these chain complexes, then the arrows go the wrong way, you see. When n decreases, n minus k increases, so they go in opposite directions, and there is no chance of homology being the same. However, this is where cohomology comes into play. And and we'll now give a definition. We're going to define a homomorphism, which we'll denote by phi k of C k of m. I will stop writing the coefficient group to C n minus k up here. So from homology, we'll go to cohomology. And we will define it as we do everything today in the only natural way that's possible. Namely, we put phi k of delta k. So our ring has a unit, so we can consider a simplex of the chain multiplied by +1. So we define this as the as delta n minus k as the cochain. So it's an element of, it's a homomorphism from C K M. Right, R C K M to R which is given by the natural formula, so dk of n minus k applied to the cell C n minus k, any cell. This is any cell. And this is equal to the correct cell. So it's equal to 1, equal to 1, if this is the correct cell. So sigma n minus k is actually equal, or is the dual to dk. We're starting from dk. So if it's dual, we'd have 1, and we write 0 otherwise. And we have the following main theorem, which will conclude today's lecture. Phi k star is a homomorphism of, so we're passing from the chain level to the homology level, of hk of m. I will write the coefficient group now, to the cohomology group n minus k of m r, and this under our conditions is an isomorphism. So we have obtained an isomorphism between the homology groups of dimension k over a manifold and the cohomology groups of dimension n minus k of the same manifold. Notice that in the case when R is actually a field, then this means that the kth cohomology groups are isomorphic to the n minus kth cohomology groups, or the kth homology groups are isomorphic to the n minus kth homology groups, because we have in the case when in this case m is finite dimensional, or this is finite dimensional, and we're in linear algebra, and everything works out quite nicely. Today I also intended to tell you about another product operation, which is called the cap product, but I have run out of time as it is. I have taken up 5 extra minutes of the allotted time to explain this. Next time, we will conclude. I'll talk about Poincare duality. Actually, this isomorphism, which is easy to prove, is, however, something which depends on the triangulation and in practice cannot be computed from this definition, from these constructions. And we will find a different way of constructing this isomorphism, which will be canonical, and which will use the so-called cup product. And that's all for today. Thank you.
And Professor? Hi, Professor, can you hear me?
Hey.
I want to ask that the video of last week haven't been uploaded.
It hasn't.
Yeah.
Okay, I will check that and I'll send you the link. I think it has been uploaded, but I will phone my colleague who does that, and I will immediately send you, as well as all the other students, the link to the previous lecture.
Okay, and may I ask, when will the video of this lecture be uploaded?
Well, I hope that it will appear before the exercise class tomorrow.
Okay.
I will ask the person who uploads the lectures to do it so that you'll be able to watch the uploaded lecture before the exercise class. Okay?
Okay, thank you. Thank you very much.
All right, goodbye.
Bye.